Okay, lastly, we're going to look at embedded systems and the Internet of Things. So realize that this is a growing trend. We're probably in the first or second inning, if you will, of what's going to be happening going forward with the Internet of Things. What are we talking about when we talk about IoT or the Internet of Things? It's adding capabilities to devices that we wouldn't ordinarily think were connected to the Internet or had any kind of computing power associated with them. So I mentioned in an earlier screencast that refrigerators, of all things, now are Wi-Fi enabled. They've become part of the Internet of Things, some models that is. Why? Well, they want to keep track of what produce is there so it doesn't go bad. Maybe it generates a list for us as to what we need to pick up at the grocery store to maintain stock in the refrigerator. So there's some value in connecting a refrigerator to the Internet. But there are also embedded systems like microwave ovens. And what's the embedded system there? Well, there's a microprocessor chip. You know, because when you go to that touch-sensitive screen to enter in the 3.5 minutes for your popcorn on high, that there's got to be a computer or a microprocessor that takes those digital inputs and converts them into signals that are used by the device itself. So those are the two things we're going to be talking about here in this last screencast for this unit: the Internet of Things and embedded systems. So an embedded system, my microwave oven was an example, is a computer hardware and software contained within a larger system designed for a specific function. And it runs the gamut. There are many, many, many different applications of embedded systems these days. Not just in the kitchen. We also have medical devices, for example, pacemakers that people might have installed. Also have embedded microprocessor chips that record the signals coming from the atria of the heart, right? The electrical signals that are used to stimulate normal heart action. Well, these are now connected to the Internet so that the doctor, your cardiologist, can assess them on a real-time basis through monitoring. Aircraft, these are obviously connected via embedded systems. The embedded systems on an aircraft are quite numerous. Many different systems are involved. Autopilot is an embedded system. That's a computer program. And many other things. Vehicles, more and more today, vehicles have a multitude of embedded signals. You're going to see that in a subsequent slide. Industrial machines, think about an Amazon warehouse where each conveyor or each stack of warehouse items has microprocessors that keeps track of what's on that shelf for inventory purposes. We also saw something like this in the Amazon Go grocery extra credit problem. Even heating, ventilation, and air conditioning systems are now connected to the Internet, and this is an embedded system in a larger system that controls your house's environment. ICS, this is a special industrial control system, form of embedded system that uses controls locally or remotely by collecting, monitoring, and processing real-time data so that machines can direct various devices in the process, valves, pumps, and motors. There's a special name for multiple ICS systems. They're called SCADA, which stands for Supervisory Control and Data Acquisition System. These have been notoriously poor when it comes to security. They could be hacked easily because these were conceived in the time before internet security or cybersecurity was a concern. So industrial control systems, an example of it might be a large-scale manufacturing food processor plant, for example. Say Cargill. Cargill is a major food producer located in the United States. They have industrial control systems, SCADA systems, that produce perhaps high fructose corn syrup from corn. Well, that is a long and involved process with many steps. You can think of boilers, you can think of valves, you can think of fluid systems. All of them have to be tightly controlled. They are controlled through an industrial control system that monitors conditions in each of those components throughout their food processing plant. If the temperature gets too high inside of a cauldron that's mixing the corn and cooking it, well, then that's going to trigger an alarm somewhere in this SCADA system on a display for a human operator who may intervene to find out what's the problem and correct it. So this is the slide I was just referring to about all the embedded systems that you might find in an automobile. It fills up the slide here. You've got an idle system, you've got cylinder deactivation, you've got blind spot detection, you've got lane departure warning, you've got seat position control, active yaw control, which determines which way the car is pointing and can detect an unsafe condition or angle with respect to the road. Night vision, driver alertness. As you can see, it's a rather extensive list of how embedded systems have made it into our automobiles. System on a chip, SoC. This is a concept that refers to how all the necessary hardware components are contained on a single microprocessor chip. So that's an important term to know. Also, RTOS, Real-Time Operating System. This is software designed for a system on a chip in an embedded system. So an example of a real-time operating system might be any device that has to respond in real time to operator input, as opposed to a static program that might be on a web page somewhere on the internet. A real-time operating system example might be, say, in a weapon system for the military. Perhaps you've got some kind of early warning radar system that operates in real time. It has to be able to display and respond to inputs from the radar operator very quickly with very little latency. Or perhaps a fire control system on board a military platform. It's using the radar information to track and target incoming projectiles to shoot them down, for example. So there has to be a computer that operates on a real-time operating system to handle that. Or perhaps in spacecraft. Spacecraft have to have real-time operating systems to respond to conditions. Think of the lunar module landing on the moon. That had a real-time operating system, primitive though it was, that needed to respond to inputs both from the astronauts and from the other sensors that were in the descent stage of the lunar module as it approached the moon's surface. It had to be able to receive signals from the landing radar and process them in the landing control operating system software to give meaningful data to the astronauts to tell them whether or not they should proceed on programmed descent or abort and return to the command module. Lastly, the slide here is talking about real-time operating systems have to be tuned to accommodate very high volumes of data that must be immediately processed for critical decision making. So the example I just gave you about the lunar module, this turned out to be an interesting issue in the Apollo 11 landing. There was a point where Neil Armstrong considered aborting the landing because the landing computer being run by this real-time operating system was running into difficulty with too much information, very large amounts of data quickly. They were getting too much information from the landing radar, and it was overloading the frames in the real-time operating system. If you want to know more about this, I will include a link in the screencast page so that you can investigate it. It's truly a fascinating computer science application having to deal with real-time operating systems and their limitations, and also how the way the priority system was set up for that actually saved the day. So let's move on to Internet of Things. What is the Internet of Things? This is, like I said, connecting every device and its mother to the Internet for the purpose of sending and receiving data to be acted upon. I once heard someone jokingly say at a conference that because of the Internet of Things, before too long, every light bulb in your house will have an IP address on the Internet. I don't think that's going to happen anytime soon, but it did convey the idea of many devices being connected to the Internet that formerly were not or even dreamed of having that kind of connectivity. It includes wearable technology and multifunctional devices. It also includes everyday home automation devices. I mentioned refrigerators. Well, it doesn't end there. Also thermostats, even coffee makers, tire sensors in your car, slow cookers. Think about that. How great it is to start up your crock pot while you're still at work before you get home so that the food's ready when you finish your commute. Keyless entry systems, washing machines, even electric toothbrushes, headphones, and sure enough, there's the light bulbs. We also, when we're talking about the Internet of Things, we talk about the body area networks. I mentioned them as personal area networks. This is a network of devices in close proximity to a person's body, like a Fitbit, things of that. Here's a graphic that shows that. You have the laptop, you have the smartphone, you have the cloud. Here's your medical professional who's monitoring the data that's being picked up from this device. Perhaps it's blood pressure, it might be vision, electrocardiogram, hearing, glucose, toxins in the body, all detected and sensed in a managed body sensor network. Also, we have autonomous body sensor networks, or ABSN. And this goes the next step, which is to introduce actuators in addition to just sensors. So not just passive, we're talking active, so that they can produce immediate effects on the body. So go back to the example of a pacemaker. If the sensor detects that the heart has skipped a beat or skipping beats, and the patient may be in distress, the device itself is probably configured to provide a jolt, but also there's actuators that could be actuated by remote sensing as well to restart the heart. So ABSN can expand the use of functional electric stimulation to restore sensation for people who perhaps have ambulatory problems or have paralyzed limbs and organs. So this would be one technique to help restore their sensation and mobility. So there are obviously some security implications here. Think of the pacemaker. If you can send a jolt to restart a heart, perhaps you can do something to stop a heart, which would be very worrisome. So reasons why IoT and embedded system devices are vulnerable. The IoT vendors, again, they're engineers, right? So that means they're all about getting something functional to market and less concerned about the security repercussions. And they want to make them as inexpensive as possible. So that's another reason why they might not spend too much time, energy, or resources on putting out security protections for us. What does this sound like? It sounds like the original internet that was created by DARPA. Remember, internet security was not even considered and was backfitted. So devices that do have security capabilities have notoriously weak security. So what does this mean? What you should be thinking here? We need a set of standards. That's what you should be thinking. Because few, if any, IoT devices have really been designed for the capacity for being updated. You know, like your smartphone and your regular desktop computer, there's a system in place to allow updates. But if you go and buy a baby monitor, is there a way to download updates for that baby monitor? Unlikely. So also IoT and embedded systems can receive patches often see long gaps between the discovery of vulnerability and a patch being applied. Why do you think that is? Why is there such, they recognize there's a vulnerability, it hits the news perhaps, but a patch takes, months. It's because they don't have the infrastructure at those companies to do cybersecurity. Perhaps you'll be one of the people that joins a company like that and helps them out. Lastly, there are several initiatives underway to address these vulnerabilities in IoT and embedded devices, and you probably guessed what one of them is. I just mentioned it. Security standards. So let's summarize what we talked about. Tablet computers are portable computing devices smaller than portable, larger than a smartphone, focused on ease of use. So we talked about portable computers, how they compare to laptops, or a laptop is really a class, I should say, a subclass of portable computers. We also talked about notebook and subnotebook. We talked about Wi-Fi as the standard connectivity method that's used for mobile devices, but there were others. There was cellular, remember the strange one, ANT, which is a proprietary one. Enterprise deployment models were how we manage this. We talked about the different deployment models. BYOD was one end of the spectrum. Corporate-owned was the other end of the spectrum. We also talked about mobile devices that can be easily lost or stolen. We talked about some safeguards there, how to protect your device. We talked about how attackers can eavesdrop on data transmissions. We looked at the two cases, data at rest, data in transit. We also looked at mobile devices that have the ability to access untrusted content, and that's a concern vulnerability-wise. And how do we manage that? We use the device management, the application management, and mobile management tools to control that at the enterprise level. We talked about minimizing the attack surface by disabling unnecessary features. We talked about lock screen, and then again with mobile device management and application management, we talked about how we can control what's on the mobile device in the enterprise and how we can change it if we need to send updates. We also, not mentioned here, talked about mobile content management, how we can communicate with our employees using the network of mobile devices we provision throughout our company or organization. Then lastly, we talked about embedded systems and the Internet of Things and what that means and what some of the security concerns are. That concludes the content for this week in Screencast. What I'd ask you to do now is to make sure you review the slides and also use the resources that are in the Cengage digital environment that are there to help you. We have the special review sections there where you can do the flashcards to help prepare for the quiz that we have this Friday, as well as the crossword puzzles and other things that help you get familiar with the terms. This particular unit is heavy on terminology and acronyms. Make sure you know those acronyms that refer to each of the various deployment models and know the brief description of what they are and what the responsibilities are for the user, that is the employee, versus the enterprise itself, the organization that's trying to manage all this content. And remember, again, I have office hours on Thursday nights when we ordinarily would have had class. That's going to be at 6 p.m. in the Zoom room. You can find the URL and password for that in Canvas. Thank you.